All right, let's dive in. Right now, inside your body, there's this incredible microscopic drama playing out. It's a story of survival, of betrayal, and transformation, as trillions of your cells are in a constant fight to adapt to stress. Today, we're going to explore exactly how they pull it off and what happens when those survival tactics go wrong.
So let's just start with the most basic question here. When things get really tough, how in the world do your cells actually survive a crisis? Because, their ability to adapt is often the only thing standing between you being healthy and you getting sick.
To really get what's going on, we have to zoom way in, right down to the cellular battlefield, where our cells are, well, pretty much always under pressure. I mean, really think about it. Everything from the air you're breathing right now to just the mechanical stress of lifting something heavy, your cells are dealing with a constant barrage of threats. So adaptation isn't some rare special event. No way. It's a nonstop process. It's the toolkit they're using every single second of every day just to keep you going.
So what's actually in this toolkit? Well, the first and most common strategies are actually pretty simple, but they're absolutely brilliant. They play some clever games with their size and their numbers.
So, first up, we've got atrophy. This is when a cell shrinks down. You can think of it like a city that's facing a famine, right? It doesn't just vanish, it downsizes. It shuts down all the non-essential services to save on resources. That's exactly what a cell does. It gets smaller to lower its energy needs, just trying to hang on until things get better. And on the complete flip side of that, you have hypertrophy. This is when a cell gets bigger. The perfect analogy is a weightlifter's muscle. It's not like you're growing more muscle cells. The individual cells you already have just get bigger and stronger to handle that extra workload. The cell basically bulks up to meet a bigger demand.
And then there's hyperplasia. Now with this one, instead of the individual cells getting bigger, the body just makes more of them. So if hypertrophy is one worker hitting the gym and getting stronger, hyperplasia is like saying, forget that, let's just hire a bigger crew. It's all about strength in numbers.
Okay, so let's just put it all together real quick. Atrophy is basically a tactical retreat, kind of like when a muscle in a cast starts to waste away. Hypertrophy is all about reinforcement, like when the heart muscle gets bigger to pump against high blood pressure. And hyperplasia? That's recruitment, like your skin building up a callus to protect itself. So you've got retreat, reinforce, or recruit. These are the body's first lines of defense, and each one is a specific answer to a specific kind of stress.
But what happens when those basic moves aren't enough? Sometimes a cell has to take a much, much bigger risk. Sometimes it has to change its entire identity. This is a process called metaplasia. Imagine you have a team of, say, highly specialized, kind of delicate workers on a factory line. And then, suddenly, the work environment gets super harsh and dangerous. What do? Well, you'd probably swap them out for a crew of more rugged, tougher workers who can actually handle the new conditions. That's metaplasia. It's a strategic and, importantly, a reversible replacement. The textbook example of this, and it's a perfect one, is what happens in a smoker's airway. Normally, you have these delicate cells with little hairs that sweep out mucus, but they just can't handle the constant assault from smoke. So the body does something clever. It swaps them out for tougher, more resilient cells. But here's the trade-off. You gain that protection, but you lose that critical cleaning function. And that's exactly where a smoker's cough comes from. It's the price the body pays for a very smart but also very costly adaptation. Okay, and this is where our story can take a really dark turn. Because these adaptations, as brilliant as they are not foolproof. So what happens when the stress just never stops? What happens when adaptation fails? Now, remember what I said a second ago? Metaplasia is reversible. If you take away the stressor, like if the smoker quits, the cells can actually change back to their original form. It's this elegant, temporary solution that just shows how incredibly resilient the body can be. But, and this is the crucial part, if that stress persists, if it just keeps going and going, that controlled, orderly process of adaptation can start to break down. The cellular machinery kind of loses control, and that orderly change starts to become disordered. That's a state called dysplasia. Now, it's not cancer yet, but it is a huge warning sign that these cells are heading down a very dangerous path.
And if the stress still continues, dysplasia can progress to anaplasia. And honestly, this is the ultimate betrayal. The cell completely loses its identity, its purpose, its connection to the cells around it. It just goes rogue. Anaplasia is a total loss of organization, and it is a defining feature of cancer. It is adaptation's final failed state. What you're left with is just chaos.
cells lose their normal shape, the whole tissue structure falls apart, and cell division just spins completely out of control. And the scariest part? Unlike those other adaptations we talked about, this change is considered irreversible. The very system that was designed for survival has now become the disease itself.
So let's just pull back for a second and look at the big picture here. Maybe from the perspective of someone who actually has to read this whole story, a pathologist.
What you start to see is that cellular adaptation isn't just one thing. It's a whole spectrum. At one end, you've got these safe, reversible responses, like a cell shrinking. But way down at the other end, you have the irreversible chaos of anaplasia. And that is why all this is so incredibly important in medicine. Because by looking at a tiny piece of tissue under a microscope, a pathologist can see exactly where a cell is on the spectrum. They are literally reading the story of what that cell has been through. And that story tells them if they're looking at a normal response to stress or the very beginning of cancer.
Which kind of leaves us with this one big, fascinating question, right? The very same system of adaptation that keeps us alive every single day is also operating on a razor's edge. So the real question is, where exactly is that line between a brilliant survival tactic and the start of a deadly disease? It's a question that scientists and doctors are working to answer every single day, one cell at a time.